Cool. So thank you for joining me. This is going to be quite a scary talk, but I think if you want to come a bit closer, it's going to have the same effect, I promise you. So we're going to take a fun trip into the darker regions of C++. My day job is doing computer vision, machine learning, working on autonomous driving systems. But at night, I work as a guide into the dungeons of C++. Now, C++ is well known as a beginner-friendly language, as I'm sure most of you are aware. But still, we still have a few sharp corners and a few very, very deep cellars. And in this talk, I had to shorten it for the 45 minutes. But we're going to meet some of the creatures that live inside the C++ cellars. So I hope you guys are brave enough to join me. If not, well, it's still not too late to go listen to some of the other fine talks here. Right. So it's going to be more or less from an A to Z list of eclectic creatures. So obviously we're going to start with A, right? So the first strange creature that we meet in C++, in the C++ type system, are called abominable function types. Now, an abominable function type is a type is a function type that's decorated with a CVRef qualifier. As we can see in the example, we're defining abominable as a function that doesn't take any arguments, returns void, and it's const volatile ref. Now, this type of function cannot exist. There is no way to actually write a function with this signature inside C++. That's not it. There is no function that can be CV qualified or a reference function, and because it's not a reference type, it's not const, and it's definitely not volatile. So why does the C++ type system allow us to declare such a type when there is no such type inside the C++ type system? And I know there are some people are trying to get rid of this abomination, but in fact, it's not that easy because this is potentially usable inside class method declarations. So I have here the proverbial rectangle struct, and I'm a very lazy developer. So, and my boss said I need to define these 6 methods called top, left, bottom, right, width, and height, which return obviously the coordinates of the rectangle. But I don't like typing out the function signatures, so I can use the abominable function type using int property. It's a function, a method, really, that's const qualified, and it returns an integer coordinate of each of these functions, right? And then I just declare all of these property methods using that signature. So I really, really hope that your code review system is going to kick this out of the repository, right? So don't ever write this. Don't say I told you. I just told you what not to do, right? Okay. So these are abominable function types. They're very strange, very esoteric, but it's fun to learn. Now, maybe the most famous and scary creature that we have inside in C++ is, of course, the nasal daemon, or the undefined behavior demons of the language. We fondly call them UB, because we like talking about the undefined behavior. I think most C++ discussions on Twitter always evolve towards undefined behavior. It has its origins, a very archaic, very ancient creature. It has its roots back in the C type system. And the main problem with undefined behavior is that it's enough to have a single case of undefined behavior to render the whole program totally invalid and meaningless. So that means, the quote from the comp stdc discussion from 1992 was, permissible undefined behavior ranges from ignoring the situation completely with unpredictable results to having demons fly out of your nose. So this was in 1992. And one of the scariest things about undefined behavior is that the compiler actively assumes that UB never happens. So whenever compiler encounters a UB situation, there's an axiom which is implicitly embedded into the way the compiler works, that this situation can never happen. And when it's encountered, basically the compiler tries to reverse engineer the logic so that, because obviously that's not undefined behavior, because undefined behavior cannot ever happen, and the whole program logic can change to make that situation not undefined. And that's how compilers can really mess up your program and completely turn your logic upside down. And last year, there was this 6-line function making the rounds on Twitter and Reddit, where it looks very innocuous code, where we're including some standard header. We're defining function as a function pointer that takes no arguments and returns an integer. We have do on the third line is going to be such a function pointer declared in global scope. And it's not even initialized because, but since it's static in global scope, it's going to be initialized to null, right? So nothing wrong here. Everything is all right. And we're defining another function called erase all. Erase all is going to return a system call which is going to erase your hard drive, right? So it's just it's going to erase your hard drive, but again, hopefully nobody's going to call that function, and no harm is going to be done. Then we have the function never called, which sets do, this global function pointer, to erase all. But again, this is only going to happen once we actually call the function never called, and we're never going to call it. Obviously, it's called never called, right? And our main function is as simple as can be imagined. It just returns the return value of do. So this is the entry point to our program. We're calling do. Do was initialized, remember, to null because it's a global function pointer, and it's default initialized. However, calling a null pointer as a function call, that's undefined behavior. And at least at the time that this was written with GCC, with a certain combination of flags, it produced this output. Now, you don't really have to understand the 3-line assembly here, but basically it would erase your hard drive. Okay, so that's what undefined behavior, that's how it can launch missiles out of your nodes, right? So that's undefined behavior. Of course, the general recommendation is make sure you run things like UB sanitizer to find a case of undefined behavior in code, because we don't. This is of course an extreme case, but it's important. It's an important lesson. I'm sure many of you have heard about duck typing. Duck typing is the term comes from the logic concept of abductive reasoning, which is colloquially known with this little poem. If it looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. And in its classical form, duck typing comes from dynamically typed languages, such as JavaScript, for example, where when the interpreter encounters a call to a function or accessing a member of an object, only then does it actually access the object and check whether that function is in its tables or whether some member exists. Now, C++ is a statically typed language, so that cannot actually happen at runtime. However, templates, at least as they are defined today, have a form of static duck typing. So whenever we instantiate a template, only then, once we know at the point of instantiation, only then does the compiler actually check whether the instantiated parameterized type supports the particular API that we're trying to use. And so duck typing, although it originates from dynamic languages, it actually exists inside C++. And one of the things that C++ concepts are trying to eradicate, or at least reduce the effect, is by having template type specification, so that we can get these warnings at the point of template definition and not at the point of instantiation. So we're not going to wait for the instantiation and the duck typing, but we're going to do it at that level of the specification. Right. So one of the less scarier and actually very welcome creatures that or things that we're going to meet today are flying saucers, or what's known as the spaceship operator. How many of you have heard about the spaceship operator? Okay, that's most of you. So it's coming to C++20. It gives us three-way comparisons, automatically generates all the comparison operators. it gives a very consistent interface. I think Simon Brand had a beautiful blog post about it last week, so I go and read that for more. And it supports a more general concepts that are not generally thought of when you're first writing comparison operators, like partial ordering and weak ordering and that kind of thing. And I think one of the coolest things about it is that if we define a struct, like the proverbial point here, which is like one of the most trivial types, all we need to do to get all of these comparison operator is just define the default comparison operator, default three-way, default spaceship operator, and the compiler will automatically not only generate those 6 comparison operator, but it will do a totally ordered member-wise comparison, which is what we would expect, basically a lexicographical comparison of each of the members in order. So I think this is beautiful. This really makes it awesome and very easy to suddenly a bunch of code for all of these basic value types gets shrunk down to a single line where we didn't even have to implement it ourselves. So I think that's beautiful, and I'm really looking forward to seeing it. Now, how many of you are aware, at least those of you who aren't on Twitter on the past couple of weeks, that we have My Little Ponies inside the C++ standard? So it turns out that when we're working on the C++20 standard, there are some atomic compare and exchange operators. Anyone who's been to one of Tony's talks yesterday spoke about the cast operator. So in certain cases, when our object is padded, then sometimes these cast operations, which compare to values, are never guaranteed to succeed. So, and the example, this is copied from the standard. So I didn't write this example myself. We have a union called Pony, which has two members. Well, they're not members, they're 2 parallel members inside the union. One is a double and one is short, and of course the short is shorter than the double, so we have some extra bits inside which are padded. And whenever we instantiate a variable of type Pony and try to run compare exchange over this type, then this might actually never succeed. So it's quite funny when we see Celestia and Luna, whoever has girls here or daughters who like My Little Pony, like my daughter, then it's really funny, but it's actually a very important aspect to be aware of. If you're doing lock-free, if you're doing concurrency, it's important to be aware that some types are not naturally amenable to using these operations. So, and there was a tweet about it, I think, a couple of weeks ago. Right, so next, terminators. How am I for time? Oh, good, okay. There are many ways for your program to die in C++. I know it's a sad occurrence, and it's sometimes very painful, but in fact, there are many ways to do it, and most of them are different from each other. And it's one of the things that's really important to be aware of and to know, and to know how to handle these. Some of these are potentially recoverable. Some of them you can intercept and at least maybe do some logging or try to recover somehow. And some of them, there's a short list of several such functions like std exit, std abort, terminate, signal, and raise. And these are only the C++ versions. There are also the C versions, and there are some platform-specific ones as well. I actually tried understanding that a couple of years ago, and I drew this diagram. The font is too small even for me to read here, because I don't actually intend for you to go into the details. You can see the yellow line here, that's normal program termination. So basically when you say return from main, this is what happens. So even that's not as trivial as it might appear, but there are many other ways to end the program. Some of them use terminate might call abort, and you can set different types of handlers and what happens when exceptions aren't caught. And there are many different ways. And again, this is really important. If you're writing robust code, if you're writing systems that should fail at least in deterministic ways, and you need to identify conditions where unexpected terminations, then there are multiple ways that you can try at least to intercept these calls and maybe extract some information for your logging systems, for debugging. So again, it's fun to think about the Terminator, but again, these are things that when you're writing robust code, you have to be aware that these things can happen. Okay, this is a bit tongue-in-cheek, the unicorns. There was a proposal called the Unified Call Syntax proposal, which, at least as of now, it wasn't accepted into C++, but I think it's a very, again, it's an interesting proposal, and it has some interesting reasoning and rationale behind it. And basically what it means is that when we're calling a function f with two arguments x and y, if there is no such function found by the function lookup, it might actually try to find on the first object x a method called f, taking the second argument as its, in this case, its first argument. So, and you might think, okay, that's weird. Why would you do that? But in fact, member functions are just sort of syntactic wrappers for a global function called with its first argument as this, as the first type. So you could think about it as a generalization of a method call, and the inverse transformation was not proposed. So if I call a method, it's not going to look for some global free function and pass the object in that way. And again, it seems a bit far-fetched, but now I'm going to give you two examples, and you see that you're actually using this every day, and you might not have noticed, is that, for example, vector has both a .begin method, and there is the global std begin, which knows how to call the container begin. Or swap often has two implementations, one as a global function and one as a method. So the idea behind this proposal was to reduce the burden of writing special code for methods and as global free functions. But again, it was relatively controversial because some people believe that it might break some legacy code. I don't want to go into that argument. But again, at the moment, it hasn't been adopted. However, I did promise you unicorns, and I can offer you this piece of code of the unicorn call syntax. I'll give you a couple seconds to read it. And I will say that Unicode character, this is Unicode characters, and many Unicode characters are valid C++ identifiers. So this code actually compiles and runs as expected. I don't know what you expect, but it runs as expected. Yeah. So we have a struct called, however you pronounce the unicorn, and you can construct it from integer. It can convert to an integer. There's a user-defined literal of a unicorn, and of course we can define 42 and return 42 from main, right? So this is a fun little example. Our next friend are VOLDEMORT types. Who here has ever heard of VOLDEMORT types? Okay, so I thought most of you will learn something. Okay, so VOLDEMORT types is a concept that comes from D, actually. I think it was the name was given by Walter Bright, one of these creators, and basically it's a type that cannot be named outside the scope of it's declared in, but it can actually be used outside, just as if you did declare it. So if you look at this simple example, we have a lambda functions create VOLDEMORT type, and I'm declaring the type VOLDEMORT as a struct inside the lambda. Right, and it just has a certain method, and I'm returning an object right here. I'm returning an object of VOLDEMORT, of the VOLDEMORT type. Now, inside our main function, there's no way that the type system doesn't give us a way to access the name of this class, because this is a type defined inside the scope of a lambda, and there's no way to get into the scope, the name of this lambda. However, if we use the auto keyword and we just said auto unnameable create VOLDEMORT type, then we can decal type on that and create a new one. We can call its methods, and everything works as we expect. So it's an interesting quirk of the language. Some object-oriented languages like Java, when you're reading about design patterns, that kind of thing, it's very common to have abstract functions which return concrete types. I didn't want to add a layer of inheritance and interfaces here, but that's definitely one of the main usages. So you can generate a concrete derived type from some known interface, and then you have this complete separation in terms of types. So nobody can actually, for example, dynamic cast it down into the type because there's no way to name this type. So it gives like a very strong decoupling of types. So again, it's a fun name, but it might actually be useful in certain contexts. Right. So we're down to Z. Okay, cool. So zombies. What happens to an object in scope after it's been moved from? Now, this might seem like a philosophical question, but it's actually a very serious question. And there is no, how should I say, there is no answer that's completely agreed upon. So some people believe the standard says that it should be valid but unspecified.
That only applies to standard library types.
Yeah. The first one, valid but unspecified, that's standard library types. Exactly. That's what yes. Although it's not always even clear what that means. I think basically it means that you can call methods that don't access any of the members.
Yeah.
Something like that, right?
Without a
Yeah.
precondition.
Yes, Peter.
Nobody hinders you that you move from states. It should still be valid, but it can be just the old state, so it would make you copy. So if you're writing your own classes, the move from state can be anything. And you might be able to call all kinds of functions on your own class because it's defined that way.
Yes, exactly. So there's not, in the library it's considered, I think
The assumption of the library is, and the assumption that you need to take with library types is it's valid but unspecified, so you can still destruct it or you can reassign a variable.
yes.
Like you can call size on it moves from vector. You
Okay.
just don't know what you're going to get. But you get a valid answer. It's probably 0 is the answer you're going to get. But you can call it. And that accesses, member variables, whatever. Because it's still a valid vector.
Okay. Okay.
With
Yeah.
vector, the chances are high, 0. With string, it might be 5.
Yeah. Small letter.
Exactly. Yeah, so but that's what I mean, that there is no single answer because you're basically, it's the typical C++ answer. We trust you, you do what you think is right in your context, right? We're not going to limit you. But again, it is a type of zombie, and it is an aspect that whenever you're writing move operations, it's something you need to consider, and somehow you don't see a lot of discussions about what happens to these husks of objects, and sometimes they do make sense, sometimes they don't. I know there was some discussion with Eric Nibbler about and Sean Parent about destructive move. Again, these are like future things that might sometimes be considered. At the moment, it's just something that you need to consider when you're writing these types which have explicit move semantics. Of course, zombies are, although they might appear so, they're unrelated to STD decay. So, it appears to be related, but it's not. However, these are not the only zombies in the language, because C++ is a very rich language, and I told you the cellars are extremely deep. So these are not the only zombies. And in fact, we have brain-eating zombies in the standard. This is taken verbatim from the standard. So go open your standard. I'm sure it's on your bedside table, right? Who has the standard on his bedside table? In your phone? Okay, at least 2 people. So you go to the index and you see brains, names that want to eat your, right? So it's actually in the standard that this is an international standard that you pay 60 euros to read, and the living dead name of zombie names. And in fact, this refers to what I say, it's the standard crypt. It's where names from the standard go to die or go to be buried, but they're actually zombies, because if you're maintaining legacy code, then I pity you, but you still have to handle auto pointer maybe, and a binary function, bind first. I just put a small list of some of these things that you'll find there. But I think that's really cool that people on the committee that they have their own kind of humor, wry humor, I guess. And these are the zombies with brains. And actually, I took out some slides because I wasn't sure about the timing. It really depends on the crowd and how. So this is my last slide, and then I have 2 more because this is an off by 2 problem here. So, there are only Bjarne said that there are only 2 kinds of languages: the ones people complain about and the ones nobody uses. And I think this is like the perfect way to end this talk because everybody here loves C++, and we all know the dark corners, but it's always good to see them and learn about them. So yeah, that's it. And I still have a few more minutes, so I'll go to the other 2. So we have shadow variables. Again, this is something goes way back to many other languages, but I think especially for beginners, it might be confusing. And if you're not a beginner, you should avoid writing this type of code. I think most compilers will emit warnings about this. And I made a really contrived example here where at the beginning, X is some kind of, it's a Boolean in the outer scope, and then inside the function, it's the name of it's a floating type, a floating point argument, and then inside the for it becomes an integer, and then inside the capture, it captures some std string, and inside the lambda, it becomes the, how do you call it, the destructuring, structured binding, thank you. Yeah, and in that case, it becomes an unsigned long. So in every scope, it actually has X refers to a totally different variable with a totally different type. And the compiler doesn't really care, but you should care. And again, this shouldn't pass code review. And most compilers will emit warnings about this. But I think it's interesting that it doesn't confuse the type system, but it will confuse your peers. So I hope that's not your goal when you're writing code. I think my last example are transparent objects. So a transparent function object accepts argument of arbitrary types and uses perfect forwarding. Basically, it allows us to create function. For example, I think that the best example is for set find. Let's say or lower bound. So they're comparison operators, which at least before we had perfect forwarding, we could only look for and find objects of the same types that a set was parameterized on. So the comparison operator would be symmetric with regards to the same type. When we got perfect forwarding, we can have what's called the transparent object, which allows us, for example, to compare an employee to an age or some integer, as long as we do have a comparison operator inside the scope that can be found by the ADL. So it's a funny name, but it's actually very common, and it's the kind of fixes to the language that make our code much easier to write and much more expressive. And the beginners, they will just write the code and it will just work. And there's no cost penalty because of perfect forwarding. It's going to be as efficient as it can be, and it's going to do the right thing. But again, it's important to know that it actually happens in the background, because otherwise, in certain cases, you'll get some strange behavior and not understand why that happens. So I think that's my list for today. In CPPCon, I actually have a totally different version of this talk with a totally other set of creatures. So if you're there, you're welcome to come and watch it. And thank you very much. And questions?